Okay, we will get started. Hello, friends. I'm Ram Lakshmanan. So I'm the architect of Ycrash Product Suite. Thank you, everyone, for attending our webinar, Java Native Memory Leaks and How to Fix Them. Right? So this is a monthly webinar series we are conducting, and thank you, everyone, for joining. So let's get started. Feel free to ask any questions at any point in time. I will answer those questions towards end of my talk. Okay. Okay. So friends, let's start off our this month's webinar with this question. Does your Java process memory utilization go beyond XMX, right? Say suppose I'm configuring my Java applications XMX, max heap size as 2 GB or 6 GB. Let's say configure as 6 GB. Will my Java process consume more than 6 GB of memory during runtime? How many of you say yes? If you say yes, put yes. How many of you say no? If you say no. Or if you're not sure, you can also say you're not sure, right? So, so how many of you think it will go beyond XMX, right? So let's find the answer to this question, right? Friends, not to find answer to this question, we need to understand the internals of JVM memory. Friends, this is probably the most important slide in my talk. And if you can understand this slide, you can understand most of JVM's internals, right? So pay attention. If you have any question, please free to bring it up. Friends, the Java process memory has one primary compartment region called as heap memory. So this heap memory has two regions. One is young generation and old generation. See, as a developer, we write code, right? We create customer object, we create account object, we create array list, hash map. All those objects goes into this young generation, which is in heap memory. And if those objects tend to live for a longer period, they get promoted to the old generation. They go to here. So our application objects, they go and they reside in this heap memory. So when you actually set XMX, you are setting only the size of this heap memory. After this, there is another major compartment in Java process memory. It's called as native memory, right? It's native memory. Friends, in native memory, our application objects are not stored. In native memory, JVM stores the metadata information, the threads or the other artifacts which is required to execute our program is stored in the native memory. Right? Let me repeat again. Our application objects are stored in the heap memory, and native memory tend to contain the information, the artifacts, the metadata which is required to execute our program is stored here. And this native memory is typically tend to be a small portion of overall Java process memory. Typically, you can go by the rule 80-20. 80% of the memory, we can say, or even 90% of a memory is heap memory. And there is this 10 to 20% typically tends to be our native memory. So what goes into this native memory? Let's look into that. Friends, the first region in this native memory is called as metaspace. See, friends, what goes into metaspace? The class definitions, right? Say I write a customer class, an account class, all those class definitions and the method definition which goes into that, they go into this metaspace, right? This is the metadata information that is required to execute the program is stored here in the metaspace. And then there's another region in native memory called as a threads. Friends, threads are a vital integral part which is required to execute our application code, right? There's a Tomcat container thread. There's a scheduled Quartz scheduler threads. And there is backend threads. There are so many threads. Where are those threads stored? Those threads are stored in this threads region, which is part of native memory. They're not stored in the heap memory, right? And then there is another region called as a code cache. See, friends, the code that as a developers we write is not the actual code that's executed by the JVM at runtime. That code gets optimized, right? And technically they call it a JIT compilation. So they do the JIT compilation to optimize our code, convert to native code, to execute it. So that optimization needs memory. Where is that memory coming from? That memory is coming from this region called as a code cache, which is once again part of native memory, which is outside of heap memory, right? And then there's another region called as direct buffer. See, friends, sometimes if you're trying to manipulate a very large objects, like say uh, image files you're trying to do, or you want to do direct memory manipulations, then people are going for this direct buffer. So you can still, instead of creating as objects, you can, if you want to do direct memory manipulations, so if you're trying to process image files or you want to do such for faster memory reads and writes, then they go for this thing called as a direct buffer, which is once again in the native memory, right? After that, there's a region called GC. Friends, in Java, the garbage collection is automatic. Not for garbage collection to run automatically, garbage collector needs memory to keep track of what objects, to references, all of them, that needs memory. And that memory is coming from this GC region, which is part of this native memory. And then there's another region called as JNI, Java Native Interface. So in case if your application is directly talking with a C or a C++ process using this JNI interface, then that memory is coming from this JNI region. Right? And friends, here I'm putting one more box called as miscellaneous, because certain JVM vendors like Azul, IBM, those kind of JVM vendors, they have certain optimizations to execute our code faster and better. They need some additional things for the JVM to execute our program. So those I'm putting as miscellaneous region. So friends, going back to this question, does Java process memory utilization goes beyond XMX? Answer is yes, because when you set XMX, you are setting only the size of your young generation and old generation. After that, there is this native memory, and this native memory has all these small regions, metaspace, threads, code cache, direct buffer, GC, JNI, and then miscellaneous. So all of them take additional memory than the XMX. So when you are doing a capacity planning, or when you're trying to allocate what should be my size of my EC2 instance, what should be the size of my Docker container, if you're doing a capacity planning, you want to give room for this XMX, and then you want to give room for all these regions. Plus, you want to give some room for the kernel processes to run. Based on that, you want to come up with the size for your Docker container memory or EC2 instance memory, right? So, friends, now let's move on to this. Let's move on to the next slide. See, what is our typical response when we get out of memory error? See, we get out of memory error, right? Friends, the out of memory error can happen even when any one of these native memory regions also saturates. Say if the metaspace saturates, an out of memory error is going to be thrown. When this threads region saturates, out of memory error is going to be thrown. When code cache is saturated, out of memory error is going to be thrown. So when out of memory can be thrown in even when any one of these regions are saturated. So what is our typical response when there's out of memory error? What do we do? In most of us, what we do is we increase XMX, right? Yes, that's what we do, right? We increase XMX. Let's see, let's say if this metaspace is saturating and now an out of memory error is thrown. Now, if you're going to try to increase XMX, will it solve the problem? Think about it. Will it solve the problem? See, now when you're increasing XMX, you're increasing heap memory size. But out of memory is happening in the metaspace region, which is a native memory. It is like if my leg is having a pain, it's like doctor is treating my hand, right? That's what it is. But friends, in this case, it's not even different treatment. What will happen is you'll worsen the problem. Think about it. Say if metaspace is having a problem, out of memory error. Now, if you increase XMX, that means this native memory is going to be even more compressed. That means the out of memory error in metaspace is going to happen even more aggressively, right? So that's why increasing XMX will not always work. And especially if it is a native memory leak, it will 100% not work. It will in fact worsen the problem. Okay. Okay. So friends, now let's do a quick recap of what is there in heap memory and what is native memory, right? So let me move here. What is stored in heap memory? Our application objects, that is the customer, account, list, hash map, vectors, those kind of objects are stored in the heap memory. What's stored in the native memory? It stores the artifacts that are required to execute our application. That is the threads, the garbage collector information, the metadata information about our class definitions. So those get stored here, right? And heap memory, friend, this is very important point to understand. The heap memory, the object's creation and the deallocation, the removing the objects from memory is done by the garbage collector. The JVM garbage collector does it. Whereas in native memory, it is managed directly by the operating system and JVM. The garbage collector does not remove the objects which is there in the native memory, but for metaspace. Metaspace is an exception. But for metaspace, it's still managed by garbage collector. But for that, like the threads, the GC, direct buffer, those all are managed by the operating system, not by it's not automatic. It's not done by the garbage collector, right? How can I set the max size for heap memory? It's one single argument, XMX. Whereas in native memory, there's no one single argument, my friend, which can set the size of native memory. So if it's metaspace, you have to use this max metaspace. For code cache, you need to use this argument. To set the max direct memory size, that is a direct buffer, you need to use this argument, right? And one more important thing I would like to say, the heap memory, accessing objects in heap memory is not as fast as native memory because it involves traversing the pointers and there's object references that needs to be managed. And JVM does that for us under the hood, right? Whereas native memory, it is direct access. It is comparatively faster than heap memory. Okay. So these are the primary difference in between heap memory and native memory. If you have any questions, feel free to put it in the chat. I will answer at the end of the conversation. Okay. So now, friends, let's understand what are the symptoms that will tell whether your application is suffering from a native memory leak or not, right? Friends, this is an heap usage, that is heap usage of an application which is suffering from an heap memory leak, right? See, the memory leak can happen on the heap memory or it can also happen on the native memory. It can happen either way, right? When there is a heap memory leak, this is how the heap usage is going to look, right? Look at this. The memory is building up. When a full garbage collection ran, it dropped. And then memory is building up and a full garbage collection ran, the memory is dropping. Once again, going up and down. But if you see towards the right end of this graph where my mouse cursor is moving, you see the garbage collector is keep on running. It's repeatedly running, but the memory is not getting reclaimed. Because there's a memory leak, the objects are building up, the garbage collector, when it runs, the memory will not get reclaimed. So this is how the heap usage will look when the memory leak is happening in the heap memory, right? But now, this is how the heap usage will look of an application suffering from a memory leak, native memory leak. Very important, native memory leak, because see, the leak is happening in the native memory. Now, if you look at the heap memory, it's going to look very normal. Look at this, it's looking very healthy. You see, it's going up and a full garbage ran, it dropped. Going up and dropping. It is if you see all the bottom points, it is coming, if I put a line connecting all the bottom points, you look at this black dotted arrow, it's going at a 0 degrees. So when there's a native memory leak is happening, you will not see any arbitrations, any degradation in the heap memory. It will look as if everything is good, right? Okay. So when there is a native memory leak, only the native memory region grows. Only native memory region grows. And friends, here is a very important point to observe. Since native memory is a very small portion, right? For most applications, we can say native memory probably is only 10%, or for some applications, it could be 20%. But there are exceptions, but typically it's going to be within the 10 to 20% range only. So if you are using your application performance monitoring tools, right, they are reporting overall memory utilization, right? They report overall memory utilization. And here in that, which includes both heap memory and native memory. And if this 10% of native memory is having an arbitration or a leak, it's not going to be visible from the most of the APM tools. That is the sad part. It's not going to be visible reported in the APM tools. So now that means how will I find out native memory leak is happening? And if native memory leak is happening, I need to narrow down which region in native memory is having a leak, because native memory has a metaspace region, it has a threads region, code cache, direct buffer, all these regions. I need to narrow down which region is having a memory leak in the native memory. So the first step is finding out whether my native memory is having a leak. Second step is which region in native memory is having a leak, right? Okay, friend, this is where native memory tracking, NMT, comes into use, right? I will talk about how to do native memory tracking in my next slide. Before that, my friends, there's a very strong indicator, right? See, when there's a native memory leak happens, and then when that native memory region saturates, an out of memory error will be thrown. And friends, there is actually 9 different types of out of memory errors. We have done a webinar about it in the past. You can go back in our archives to look at it. There are 9 different types of out of memory error. Based on which region the out of memory error is happening, that particular out of memory error is going to be thrown. See, look at this. Here, if an out of memory error is happening at the metaspace, let's say metaspace is saturated, that means an out of memory error is going to be thrown like this: Java lang out of memory error colon metaspace. So when you see this out of memory error happening, it means it's indicating the memory leak is happening in the metaspace region, right? And if the memory leak is happening in the threads region, that means this out of memory error will be thrown. Out of memory error, unable to create new native thread. This error is going to be thrown. And then if the memory leak is going to be happening in the direct memory region, it's going to happen in the direct memory region, direct buffer region. That means this is the error going to be thrown. Direct buffer memory, out of memory error, direct buffer memory is going to be. If the memory leak is happening in the code cache region, you're going to be thrown out of memory error, code cache full. This is the message going to be thrown. So based on what type of out of memory error you're getting, you would be able to know which region in the memory is leaking, right? So that is a clear indication. It could be leaking or you're under allocated the memory. It could be either one of the reason, right? But this is more reactive, right? Out of memory has already happened. That means the problem has already manifested in your application. How can I see that problem, catch the problem before, even if it results before it manifests as an out of memory error? Can I catch it early? Yes, you can catch it early by doing this native memory tracking. How to do the native memory tracking? Details about it can be found in this blog post, but I will give you an overview of how to do the native memory tracking. Friends, in order to track this native memory, you want to pass this flag when you start your JVM. Say, suppose I'm starting my Java application like this. You want to add this -xxx, native memory tracking is equal to summary. You need to pass this JVM flag to your application. When you pass, then the JVM will start to record native memory utilization. It will start to track it. And then what you want to do, my friends, is you want to, on a periodic interval, like say every 10 minutes, say for 24 hours period, what you want to do, you want to execute this command, say jcmd pid, that is what is your Java process, with which you launched your application, right? You give that, and then pass this argument, and then pipe its output to this file, to any file. You can give it as I'm calling it nmt report.txt. So what is this command, jcmd command, it will do is, it will now connect with the JVM, and then it will take what is the native memory, each region's size at this point in time, and then write it to nmt.report.txt. It's going to write it here. And then for every 10 minutes, it's going to connect, get the data, what is the size of each native memory region, and then it's going to print it to this file. It's going to keep on appending to the file. So now you can open this nmt report.txt in your text editor, or you can use our GCEC tool, right? To this GCEC tool, you can upload this nmt report.txt which you captured. So now the tool will analyze this data, and then it will tell whether any leak is happening in any particular region or not. So let's look into a sample native memory report, right? How does it look? So let me open a sample native memory report file. See, this is how that file is going to look. See, you see, it's going to print each native memory, all the JVM regions. What is the heap size? What is the class, which is metaspace? What is the threads? What is the code cache? GC. It prints all these regions. What is the size, allocated size? It keeps on printing like this, right? So it's going to be a little tedious to look into this text editor, but you're most welcome to do it in a text editor as well. But now what we'll do, we will upload this to the GCEC tool and see what it is reporting. So now I'm going to be uploading to the GCC tool. So friends, our tool set is available both on the cloud and as well as on the prem. You can do either way, right? Some people classify these as production artifacts, so they don't upload it online. So rather, they can just they can have the tool installed locally, and then they can do the analysis as well. So now I selected my file. Now when I uploaded, look at this. If any suspects, memory leak suspects are found, it's going to be reporting here. See, look at this. It's suspecting that two regions are suffering from or consistently growing. It's a memory leak suspect. The heap region and then the thread region says that. And also if there's any over allocations have happened of memory, it also reports that. So now it gives me all the regions. What is my heap size? Metaspace, threads, code cache, what is it committed, and what is it actually reserved. So reserved means that's what has been allocated. Committed means that's what being currently used at this point in time, right? So now let's look at here. Let's look into the threads region, which is reported as a leak is suspected. Look at this, my friends. For this application, the reserved size is 60 kilobytes. But now you see the trend. The threads usage is consistently going higher and higher and higher, right? You can see if it is going like this, keep on increasing, that means it is suspicious. There could be a potential memory leak. And when this exceeds the allocated size, then you're going to get out of memory error, right? So this is a very simple and effective way to see which native memory region is leaking to identify in a proactive way. But reactively, once if it has saturated, you're going to out of memory error is going to be thrown. In the out of memory error, check what is the type. Then based on that, we can go and address the problem. Okay. So now, my friends, let's look into some of the common native memory leaks, right? So these are all the regions in native memory. There is a metaspace, threads, code cache, direct buffer, garbage collector, JNA, miscellaneous. So friends, in this, the leaks, the memory leaks typically happens only in these three regions: metaspace, threads, and direct buffer. Because these three regions are the ones that we developers fiddle with, we manage. Others are managed by JVM itself. So typically the JVM developers, they're pretty good, right? They don't have 99.99% of case, they don't have any problem, right? See, because the code cache is basically the hotspot compilation. So there won't be any leak here. Similarly, the garbage collector. If garbage collector has a memory leak, that's a very, very serious problem, right? So that will not happen. Most of our applications, we don't use JNI. That is, we don't directly connect with C and C++. We don't use JNI. So these miscellaneous regions are all managed by the JVM vendors itself. So they don't have any issues. If at all the memory leak is going to happen in metaspace or the threads or direct buffer, because this is what we as application developers fiddle with it, right? So now in the remainder of this session, we'll talk about what causes this memory leak, how to go about fixing them, what are the potential solutions. So that's what we're going to be talking, right? Friends, first let's talk about the thread leaks. The threads can have a leak, right? If threads can have a leak, when this happens, out of memory error, unable to create new native threads are going to be thrown. Friends, when this happens, right, it means it's indicating that threads are leaking in the application. Say typically your application has like a 203 in the threads. Maybe the thread count is going high, like a 400, 500, 1000, 2000, like that is going high. It can happen. When it happens, we are going to be seeing our application is going to confront out of memory error, unable to create new native threads. When this happens, what is the artifact that we need to troubleshoot? What is the artifact we need to troubleshoot when we see this out of memory, unable to create new native threads? Will heap dump, will it work? No, heap dump will not work because heap dump is a snapshot of memory. What are the objects in memory? It's going to take and then it's going to analyze. But thread leaks means what you want is you want to take thread dump from the application. The thread dump tells what are the threads running in the, how many threads are there in the application, what are the threads, what stack trace they are executing. It's going to contain all this information. So you want to capture a thread dump when you confront out of memory error, unable to create new native threads. How to take a thread dump? Friends, there are 9 different options to take a thread dump. Here's a blog post which walks you through it. But friends, here I want to share with you a very effective technique or open source script. There is this open source script which we have contributed called as a YC360 script. It's available in the GitHub. So friends, when you trigger this script captures 360-degree artifacts from your application stack. See friends, no one is going to come and say, oh, your application is having an out-of-memory error, unable to create new native threads. So that means a leak is happening in the threads. So go ahead and capture thread dump. No, what we get is, oh, the application has crashed. Your application has become unresponsive. That's what we get. And when we get that kind of a statement, the problem can happen because of anywhere. There could be a thread leak. There could be an object leak. There could be a long-running garbage collection log. There could be a network latency. There could be a backend slowdown. Anywhere, anything could have gone wrong. So best way to troubleshoot any production problem is to equip yourself with a 360-degree data. So what is a 360-degree data? The number one, the most powerful artifact that we use for troubleshooting production problems is application logs. And then the thread dumps, heap dump, heap substitute, garbage collection log, if netstat, vmstat, iostat. So this script captures all these data and then bundles them as a one single zip file for you, as a one single zip file. And now we can take the zip file and then you can do analysis. And this is an open source script. You can consider leveraging it to troubleshoot any production problems. Okay. So now, if you see, one of the artifacts the script captures thread dump, which is the artifact we need to troubleshoot thread leaks, which is happening in the native memory, right? So now what I will do, I have gotten here a real world case study. So this is a problem, a thread leak that happened in a very major financial institution in North America, right? So what happened was this middleware, as you know, middleware has to be highly available, right? It has to be highly available, even 99.999. If middleware has any hiccups or it goes down, none of the channels, none of the business units will not work, right? They will stall. So the availability has to be very high. And this middleware had a thread leak. So it started slowing down. Now let's look into that actual thread dump, which was captured from this middleware. And then let's look into that. Okay. So let me go. Okay. So friends, this is the thread dump, which was captured, right? See, this is a pretty tedious file, right? Looking at, it's a text information. It's pretty tedious to analyze, look into that. So what you can do, you can use like thread dump analysis tools. Like one of them is FastThread, made by our company. So now to this tool, if you upload the thread dump, this thread dump analyzer analyzes a thread dump from various aspects. It applies various pattern recognitions to see whether any problems are happening in your application. So now let's upload this thread dump and then let's see what's getting reported. Okay, so now I upload, the tool is analyzing. Initially, it reports a problem. You see, it's reporting at the very top. Oh, there are 1,700 plus threads are stuck waiting for response from Oracle database. It can slow down the transaction, review the stack trace. It's reporting that problem, right? So now, friends, look at this. This application is having, at the moment when the thread dump was captured, like a 1,859 threads. On a normal day, this application has only around 300 or 400 threads. That's what it has. Now it is having 4x, 5x more threads, right? See, now, see the tool as gives multiple analysis from multiple perspective. But let me just move on to an important section here. It's called as a last executed methods. See, friends, I told this tool does a lot of pattern recognitions, right? It sees whether there are any patterns. If the patterns are there, then it reports to us. So one of the pattern is all roads lead to Rome. See, friends, some of you are joined from Europe, right? When Roman Empire was at its peak power, they built the roads. They were built such a way that finally all the roads comes to the Rome for better transportation. That's how it's been architected, right? So friends, similarly, if in your application, if there's any bottleneck, right? Say here is a bottleneck. That means what will happen? Multiple threads will start to navigate and they come and they get stuck on that bottleneck. So it doesn't matter where your thread origins. They will origin some multiple places. But if there's a bottleneck, they'll come and they collide on one particular method or where the bottleneck is there. So this uh, this pattern checks whether as multiple threads are coming and they're coming and colliding on a particular method or particular point in your source code. And apparently it turns out to be the case. Even though this application has like 1,000, even though it has like 1,859 threads, you can see 1,700 threads. That is 92% of the threads of this application or ending up in this method socket read. That's where it's ending up. So now let's look into this. 92% of the threads are ending up here. Let's see the stack trace. Let's look at this. This is the stack trace. You can see it is originating from the Oracle package. See, what had happened was, look at this, originating from the Oracle package, and then now it's going and they're getting stuck. They're trying to read and they're getting stuck. See, friends, what had happened? Look at this. There is this ONS, right, which stands for Online Notification Service. So the database vendor, the Oracle, the database vendor, told to this middleware platform, hello middleware platform, because your availability has to be very high, you turn on the flag called as ONS, Online Notification Service. So this middleware talks with various system of records. One of the primary system of record is an Oracle RAC cluster. So the Oracle team told to this middleware team saying, enable this flag ONS to be true on your JDBC driver in your middleware. So when you enable to true, what's going to happen is if your any one of the node in the Oracle RAC cluster slows down or has any hiccups, immediately the very next transaction will be routed to the other active node in the cluster. So your availability will get better. So this middleware team also followed the advice and then they enabled the flag to be true. When they did it, actually contrary happened to what the vendor told. What happened was when the flag was enabled to be true, a new thread was spawned for every transaction, but the thread was never terminated. So thread was not. So as time grows up, that thread started to build up. Thread started to build up. So that's why they ended up having like thousands and thousands of threads. So when so many threads are created, you are going to saturate your threads region. So when the threads region is saturated, application is going to throw out of memory error, unable to create new native threads. After seeing this, they reported, after seeing this error, saying like thousands of threads are waiting on this ONS Oracle driver package. They reported to the vendor, the Oracle vendor. Then the Oracle vendor, they acknowledge, oh, sorry, we are trying to pilot a new feature. So we tried it on you. Looks like it's not working. Sorry. So then they gave a patch. Once they installed a new JDBC driver, the problem went away. Okay. Yeah. So that was the issue. So now let's do a quick recap. How you are going to approach the problem when you're going to get out of memory error, unable to create new native threads. What you're going to do. So, my friends, it indicates when you see this error, it indicates the thread is leaking. Objects are not leaking. Heap is very nice. So the threads are leaking. That's what it's indicating. What are the solutions to fix this problem when you see this one? When you see this out of memory error? What you want to do is you want to fix a thread leak. That is, you want to take a thread dump and see whether any really threads are leaking. If that is the case, you want to fix it. Friends, and sometimes, what is the second solution? Friends, sometimes what happens is our operating system enforces a limit saying every process can create only 512 threads. every process can create only 256 threads. There's a limit set at the operating system level. And what if the operating system has set a limit, only 512 threads can be created? What if my application genuinely needs more than 512 threads? Genuinely it needs. In that case, if it goes to try to create the 513th thread, at that point, JVM will throw this unable to create new native threads. In that case, what you want to do is you want to use the ulimit command and increase that limit. Instead of keeping as 512 as a limit, increase it by 1024. That could be a second potential solution if you need a genuine more number of threads. Friends, the third solution is, see, look at this. Then the threads are in the native memory region. Friends, here is one very important takeaway what you want to take, right? Let's go back to this diagram. Let's go back to this diagram. Friends, this native memory, you can set the limit on metaspace, code cache, direct buffer. But you cannot set a limit on threads. There is no limit on the threads. It can keep on growing till whatever your RAM capacity is. It can keep on growing till whatever RAM capacity is, right? So, what if in your RAM, in your memory, at midnight, 12 a.m., you're launching a cron job, or you're launching some script, and that script starts to consume more memory in the device. If it starts consuming more memory, that means now the threads during the daytime, maybe it would have sufficient memory, but the night time, because your cron job is running, it may not have sufficient memory. So that means at night time, you may start to see this unable to create new native threads because the cron jobs are running. There's nothing wrong in my application. My application is going fine, but just because cron jobs are running, they tend to occupy memory. So my application now doesn't have enough memory to create threads. This can also happen. When this happens, what is the thing you want to see? So that's why one of the solutions that has been highlighted here is, kill the other processes. Say if there's a cron job is running and eating up the memory, kill them, remove them, so that you get to create a room for your threads, right? The fourth solution is increase your RAM capacity. Increase it because your application needs genuinely more threads. Increase the RAM capacity. Fifth solution, this is a little bit interesting. What you can do, you can reduce your heap size. That is, reduce your XMX. When you reduce your XMX, that means now your native memory is getting bigger, right? So now you can create more threads. So that is another possibility. The sixth solution is you can reduce your stack size. See, friends, each thread has a stack size, right? I set it to the parameter called XSS. Say I set it as 1 MB, XSS as 1 MB. That means each thread is going to occupy 1 MB space, right? Say suppose my application is creating 1000 threads. For XSS, if I can as 1 MB, that means I need 1000 MB of space, 1 gigabyte I need. But what if I reduce my XSS to be 512 kilobytes? Instead of 1 MB, I reduce to 512 kilobytes. If I reduce to 512 kilobytes, that means to create 1000 threads, I don't need 1000 MB, I just need 512 MB. That means now I can create more threads, right? That's another solution, but be careful. If you reduce your stack size, you may confront stack overflow error, right? You may confront the stack overflow error. Okay. So what is the artifact you need to troubleshoot this problem when you get this out of memory error? You need thread dumps. Heap dumps will not help you. So what are the tools that you need to analyze this artifact thread dump? You can use thread dump analysis tools like a fast thread, or you can use text editors. Open in text editor and then you can look into it. Okay. Friends, now let's look into the second type of out of memory error. A second type of memory leak that's happening in native memory, which is the metaspace. Friends, what is stored in metaspace? Metaspace stores our class definitions, method definitions, our static variables. All those, they go into the metaspace. The metadata definition required to execute our program is stored here, right? So this region can also have a leak. So friends, here is a real world case study of an application which was suffering from a metaspace memory leak due to a Kotlin library. So there is this one Kotlin library which is it's a real world case study. You can look into the link and look into that. It was happening in one microservices. So this Kotlin library was used to connect with the backend system and get the response. So what this Kotlin library was doing was, for all the calls that was going and coming back, it was creating new class definitions. For all the object that was coming back, it was creating new class definitions. Whenever new class definitions are created, where it's stored? It's going to be stored in the metaspace. And when the metaspace region was saturated, they were getting this out of memory error metaspace. They are getting that error. So look into this case study. It's going to be very interesting. But now for our discussion, I'm going to show you a simple demo, right, of triggering this metaspace, right? Let's look into that. So I'm going to be looking at. See, friends, look at this. This is my program. This is my sample program, which is going to create a metaspace memory leak, right? Now look at this. So here I have this main method. Look at this, my friends. So what I'm doing, I'm having an infinite while loop. Right? I'm an infinite while loop. Look at what I'm doing. I'm saying I'm just creating a new class name, say com metaspace object, and then a counter. Right? Initially it starts with -1, and then I'm incrementing the counter. So I'm creating a new class definition, and then here I'm saying make a new class. So when the thread comes first time, I'm going to create a new class by name, com buggy up metaspace object 1. And now on the next iteration, it's going to create com buggy up metaspace object 2. So you want to keep on creating new classes. Where are the class definitions stored? The class definitions are going to be stored in the metaspace. So I keep on adding new class definitions. When I keep on adding new class definitions, when I go beyond that metaspace limit, then I'm going to be then Jim is going to throw out of memory error metaspace. So let's run this program. So let me run this program. Okay, so I'm running. See, for every 5,000 new classes created, I'm just printing here. So you see it says 90,000 new classes created, 100,000 new classes created. So it just keeps on printing like that. Okay. It just keeps going. Okay, so now after like a 290,000 objects, 290,000 classes, it's struggling. And then now it's throwing Java lang out of memory error metaspace, right? Friends, sometimes, see, here I'm intentionally simulating and creating this problem. But sometimes, my friend, this error can happen genuinely also it can happen. See, think about it. My application keeps growing, right? I keep adding new libraries. I add a Spring library, Hibernate library. Now I'm adding a LangChain AI library, right? Whenever you add those third-party jar files, each jar file is new class definitions. All those new class definitions are going to metaspace. What if you are not allocated sufficient metaspace? Then you're going to get this out of memory metaspace, right? Now you want to, what you want to do, how to troubleshoot this problem. So now, my friends, to troubleshoot this problem, what you want to do, you want to pass this flag to your application when you launch. If you're running on Java 8 or before versions, pass this argument, verbose class. If you are running from Java 9, pass this class, pass this argument. So when you do that, what JVM will do is, JVM is going to print every class that is loaded into memory is going to be printed, and the console is going to be printed into this file. So it loads a class A, class B, class C. It's going to print everything. And if you typically see, if you see particular package is loading a lot of classes, that's a classic indication that this is the package which is causing the memory pressure on the metaspace region. So now what I will do, I will pass this argument. Let me open this verbose class argument. See, okay, so here I'm going to launch the same program, but now I'm going to be passing this verbose class argument. So it's going to print all the class definition that is loaded into memory. So now let me run this program. Again, the very same program now I'm running. Look at this. When I ran, look, it's printing, oh, it's loading this object. It's printing what object is getting loaded. So with this, I know, oh, okay, it is originating from this particular package. So then I can narrow down and then I can go ahead and fix it, right? So this is an effective way to troubleshoot out of memory error metaspace, right? Okay. So now let me come back. So let's do a quick recap of how to go about troubleshooting out of memory error metaspace, which is a pretty common native memory leak, right? What causes it? When I try to create large number of dynamic classes, like for example, the Java, we use the Java reflections to create load new class definitions. You're going to see this error. Second reason why it can happen is maybe I'm loading a lot of third-party classes, third-party jars, third-party frameworks, and keep on loading, and I don't have sufficient metaspace. Then you're going to confront this out of memory error metaspace. And the third reason is, what if I'm loading a lot of class loaders? I'm having a lot of class loaders. Each class loader is loading. Then also I'm going to get this problem, right? What are the solutions? See whether if it is because of a memory leak in the code, then fix it. Like in this case, I'm just going on a loop and keep on creating the classes, which is not the right thing. That should be commented out. Sometimes, genuinely, it could be organic growth. Maybe an application has been growing and adding a lot of third-party jars and sufficient metaspace is not allocated. Then you'll get this error. In that case, increase your metaspace size with these arguments, right? So what is the artifact you need to troubleshoot it? So if you're running on Java 8, pass this verbose class. Your Java 9 and above, pass this argument, right? There is also a couple of more approaches are here, but these two are pretty effective and simple techniques you can do. And then what are the tools you need? If you're just doing this one, there's enabling this arguments, just a text editor is good enough for you to see what is the problem going on. Okay, my friends, now the third type of native memory leak that we are going to discuss is direct buffer, right? Direct buffer is the region where if you want to do a direct memory manipulation, people are start doing if I want to do image processing, PDF processing. In fact, there's a lot of caches are running here on the direct buffer region for faster read writes, right? If you're directly reading, if you're directly doing the memory access, then and if there's not sufficient memory allocated in the direct buffer region, you will confront this error. So now let's look into an error. Let's look into a demo, right? Let's look into a demo, which is going to trigger this type of out of memory error. Okay, and look at this source code. Look what I'm doing. I'm using this library, this API called byte buffer, which is part of Java native IO. So when I use this byte buffer and I'm trying to allocate memory, this is going to be allocated in the direct buffer region, which is the native memory region, right? Look at this, what I'm trying to allocate a very large size of memory. What if there's not sufficient that memory is there? Then I'm going to be thrown this out of memory error direct buffer. So let me run this program. So when I run this program, see, immediately the error gets printed. Java lang out of direct buffer memory. Friends, one very nice thing is when this direct buffer memory happens, it prints a stack trace. So the stack trace clearly points which line of code is causing it. So here I can see, oh, here there's this OOM direct buffer. In the main method, in the line number 10, it's saying it's trying to allocate a very large size memory buffer, which is not there. So out of memory error is shown. So when you get this out of memory error, look into the stack trace to see where it is happening. See whether they're genuinely doing it or whether there's because of some bugs or anything is happening. Then we can go to this particular line and then fix the problem. Okay. So now here is a quick recap of this out of memory direct buffer memory, right? So friend, this happens when there is an increase in the direct buffer usage or when there is a leak. That is whenever I use these packages, NIO package or image processing, or when I do these kind of libraries, they are directly work with the direct buffer region. That's when I want to confront this error. How to fix it? If it is a memory leak, fix the code because look into the stack trace and where it's happening and then fix it. Or sometimes what happens is maybe you have allocated a very small size. The default, I think I don't know, it varies by the JVM, but say if default is not sufficient, increase the size, max direct memory size, do that, right? And friends, increasingly, the workload in modern frameworks, they're shifting from the heap memory to this direct buffer, especially the Spring. They moved in the modern versions, they deprecated the REST template. If you're using a REST API, there's two ways you can use the Spring's REST API. One is through REST template, other is through the web client. So they are deprecating REST template and moving to web client. But with the web client, what happens is the workload is shifted from heap memory to this direct buffer region. They're moving it here for faster read-write access. So that means workload is moving. So say suppose you so if you move from REST template web client for REST APIs, you need to be aware of this region. You need to check whether you have allocated sufficient memory for this direct buffer region. If not, increase it. Also, since noticing a lot of frameworks are evolving and they're moving the workload to this direct buffer region, the Java, they have made a lot of significant upgrades and the performance optimizations to this region starting from 11. Starting from 17. Starting from Java 17, they made a lot of upgrades in Java 17 for this direct buffer region. What is the artifact that you need to troubleshoot the problem? I need application log, because or std because the stack trace is only printed. Or you can also do the native memory tracking, right? To see whether it is keep on growing, can do, and then you can take a corrective action. You don't need any special tools to troubleshoot this direct buffer out of memory error, right? Okay, friends. So I'm going to tell you all a good news. My session is ending now, right? I'm here to take any additional questions, but before I wrap up, in case if you're not bored with this session and if you want to enrich your knowledge on JVM performance engineering and tuning, here is an online class which is available. It's a recorded training program. There is 8.5 hours of recorded contents about GC tuning, about troubleshooting out of memory error, how to troubleshoot production performance from thread dump analysis, heap dump analysis. It goes pretty deep. If you want, you can enroll here and then you can study about JVM performance tuning. Okay, my friends, thank you everyone for attending this month's webinar.